Good morning, welcome. My name is Michalik. I'm a principal engineer at Rabobank, and I want to take you down the rabbit hole, a rabbit hole of text processing. When we come out of this rabbit hole, you will know everything you need to know about safe text processing and about Unicode. So let's get to it. We have one objective for today: turn letters into bytes, and then turn bytes back into letters the same way that the original author intended. So imagine that. You are fresh out of school, you are first hired in your first job, and you get a task. Design how to encode letters in a computer. You sit down, you write the alphabet down, A, B, C, down to Z, you put the numbers in, maybe throw in a few punctuation marks. You round it up to maybe 100, and for the rest of the day you watch YouTube. At the end of the day, you come to your boss, you show him the table. He says, well, that's good, that's good. This is just enough what we need, right? I think so, yeah. And if it's 1963, you did a very good job. You just invented ASCII. If you speak English, and if it's just the beginning of this whole computer thing, used by scientists mostly, if the computers have only 7 bits in a byte, you did a perfect job for your use case. Especially if you have to support this pesky thing called teleprinter. So a teleprinter is, it's from beyond my time. What I read, a teleprinter is a typewriter plugged into a cable. So you want to also, apart from the letters, you want to also control that teleprinter within your encoding. So you dedicate the first quarter of your encoding scheme of those precious 7 bits that you have to teleprinter control. All those line feeds, moving the carré left and right, and ringing the bell maybe. Sorry, that's fixed. You cannot use it. And nowadays, you cannot use it for anything else ever again. And you think, that's enough? All the letters, A to Z? No one else will ever need more. Unless you're unfortunate and speak a language other than English. So what you see here, I'm Polish, and in Polish we have a few letters that are not in scope of the original English alphabet. All those little dots and commas and little hooks on the letters. The sentence in the topic of the slide, zarzuć gęślą jaźń, it doesn't make sense at all. But it uses all the letters that are there additional in the Polish language, all the diacritical marks. So imagine that you also need to support some, maybe just the Latin alphabets, other than English. Luckily, the bytes just got extended to 8 bits, and this became a standard. So you have 128 characters more. And does it really matter to use those additional national specific characters? Well, to me it does, because this little dot above Z, it makes a difference between ribs and a zebra, or between beggars and multiple zebras. So it's actually nice to have those specific diacritical marks. Well, how do I support multiple languages? Polish has those few additional diacritical marks, other languages have others. And we have a limited set of bits in a byte still. What we always do, we send metadata. We say, the upcoming text is going to be in Polish, or it will be in Norwegian, or it will be Greek, and the extra 128 bits or 128 characters that we have, thanks to the extended byte, we can use them for that particular encoding. You declare the encoding first, as in HTML used to be, and the whole HTML page is in that encoding. Nice. The same value, though, can mean different things depending on what you declare. So if you put in value 230, if you declared it as Polish, it's tju. If you declared it's Norwegian, as good as my Norwegian might be, it's a, probably. And if it's Greek, it's letter zeta. And if you didn't say anything, what is that garbage? Well, you will maybe get garbage on the screen, or the browser, if it's HTML, might do some smart analysis of the text and figure out statistically, looking at those extended letters that you are using, it probably is Polish. If it's not, then tough luck, you still get garbage. Now, using that approach, you wouldn't be able to publish a book with proverbs from around the world, which would use multiple alphabets. English is your default, but how do you mix it with Chinese characters? With the transliteration of the Chinese characters, with all those marks pointing the accents? How do you mix it with Polish and all the other possible scripts, Greek, Cyrillic alphabets? Declaring just one metadata for the whole text is not enough. Throw in a few mathematical formulas too. So let's clarify a few words. Within the scope of this talk, a character is a very abstract meaning. We define it as the smallest component of written language that has some semantic value. It's an abstract thought, like Platonic idea, but in different contexts, it might mean different things. So when you see a word character, it's always a bit, you should be suspicious what the author might mean behind that. Now, if you move into the typesetting context, you have a glyph, which is basically a picture, a representation on screen or on paper of a character. And you have a font which is all the glyphs that look maybe the same. Shifting towards our actual topic, encoding characters, we have a code space, which is the range of the values that we can assign to our characters. So your initial example with putting the letters A to Z up to 100, that's our code space of 100 positions. Later on, we have 256 positions in the ASCII extended code space. A single value in that code space is a code point, and we will use that name often today. An unencoded character or character encoding is the mapping between the character and the value in the code space. Now, having that out of the way, we want to improve on our ASCII scheme. We want to support more languages. Easy. Just collect them all, right? All the languages from the whole world, all the symbols that people might be using, yes, emojis too. Write them down in some order, put some padding between you maybe don't want to mix Chinese with English alphabet and emojis. Put them in nice little blocks. Assign numbers from your code space 1 to how many you don't know, and you're done. And you just invented Unicode. Congrats. It's 1991. And the Unicode people decide, right now, in the current usage, there's undoubtedly below 2 to the 14th characters in use, all around the world. If we take all the books, all the newspapers, anything that is published right now, that's under 16,000 characters. Go back to the first slide with Padme. You know where this is going. So we are at version 15.1, and they increased the number of characters by a bit. So this one I will read out literally as it is written on the Unicode main page. Unicode covers all the characters from all the writing systems in the world, modern and ancient. It also includes technical symbols, punctuations, and many other characters used in writing text. The Unicode standard is intended to support the needs for all users, all types of users, whether in business or academia, using mainstream or minority scripts. Mainly, we want to cover it all. And with the reserved character space of 1.1 million and only 150 characters actually in use, well, they have enough of a breathing room to add missing characters if anybody ever comes up with one. And here, character is really a unit of information. It's not a picture of a letter A. It's more of a concept of a letter A. So you saw that the versions of Unicode, they grew over time, and that had reflection in Java. If you just look at the Java doc of the character class, you will see which version is supported in the current JDK. And with the Java 20 release, Unicode version 15.0 is supported. The latest version of Unicode 15.1 was just released in September, I believe, so unfortunately they didn't make it to Java 21. But depending on the Java version that you are running, it might behave differently when certain Unicode input is entered into the system. Now we really get to the computer stuff. Only from now on, we start thinking about bytes. Earlier, it was just an abstract mapping between some abstract characters again and integers. So Unicode reserves 1.1 million code points. That would fit in 3 bytes. However, computers don't really work with 3 bytes at a time, so let's just extend it to 4 bytes. And let's make a mapping between our Unicode table, the code space, and 4 bytes, somehow. We define a Unicode transformation format, UTF. And again, the simplest approach is super easy. You have a letter, it has a certain position in the Unicode code space, like letter A has position hexadecimal 41. Well, you write it in 4 bytes as many zeros, 41 at the end. Good job. You invented UTF-32. 32, you use always 32 bits to encode a character. Unfortunately, that's quite a lot of zeros for a letter A. But we have our first encoding. Now, let's try to cut down on those zeros, because all the ASCII letters, they are actually pretty commonly used. So we would be throwing away a lot of space on the network, on the disk, just to store those zeros if we use UTF-32. One of the initial ideas was UTF-16, a bit more sophisticated. Well, originating from the thought that undoubtedly below 2 to the 14th is the number of characters that we want to cover, well, 16 bits should suffice, right? So Unicode works with big blocks of characters that are somewhat similar to each other, and they call it planes. And the most important plane is called the basic multilingual plane. There we store all the Latin alphabets. We store, for example, most of the Chinese, Japanese, and Korean characters, the ones that are in most use. What is in the current use in the whole world would fit in just this one plane. And it just takes 2 to the 16th code points. So if you write down all the characters that you want to encode, there is still some room left on that plane. And you can use a little bit of that room for some technical magic. So let's take 8 of those little blocks. Each of them represents 256 code points. And let's say that if you combine 1 block from the first 4 and 1 block from the latter 4, you do some bitwise shifting, then you can generate the rest of the Unicode code space. Right? You call this surrogates. The first 4 are the high surrogates, the second 4 are the low surrogates. You combine one of each, and you can generate the rest. Amazing idea. So the most used characters, you only encode using 2 bytes, 16 bits, and you can generate the rest of the lesser used characters by combining 2 of those 2-byte characters. However, in the end, the world decided UTF-8 is the way to go. UTF-8 is a dynamic encoding. Depending on which code point you want to encode, you use 1, 2, 3, or 4 bytes. And you can see the first, the ASCII characters, you encode as just 1 byte. It's ASCII compatible, 7 bits. Now, if UTF encoding starts with a 0, it means it's the ASCII character. If it starts with a 1, it means that it's going to be a dynamic encoding, and the number of 1s after this first one says how many bytes we will have to encode this character. So if we need 11 bits to encode a particular character, well then 2 bytes is enough, we encode it like that. If we encode a character somewhere from the very end of the Unicode code space, we need all the 21 bits, we use it like that. And 21 bits would be enough to encode any Unicode character, but that again would be a waste. So it's a nice way to compress using some heuristics basing on which characters are used the most. And the ones that are at the beginning of the Unicode code space, they are used the most. So here's a little comparison between the 3 possible encodings. The plain ASCII letter A, you encode in just 1 byte in UTF-8, 2 bytes in UTF-16, 4 bytes in UTF-32. If you go beyond ASCII, then it starts growing, but you can see UTF-16 handles the Latin scripts, handles Korean script, it would handle a lot of the Chinese and Japanese scripts. Only if you go very far in the Unicode code space, you need 2 UTF-16 surrogates to build up that code point. And as you go down the Unicode code space, you also need more UTF-8 bytes. Now, the most important thing from this talk is that the encoding is made explicit. So we often just use plain text, or just send string, or just convert string to bytes and bytes to string. And somehow it works. But take a moment to think about it. Am I explicit enough in saying that it is UTF-8, which is basically what everybody is defaulting to? If you set up a database, make sure to explicitly say, store the strings as UTF-8. Because sometime, somewhere, maybe a tester, maybe some malicious user, or maybe somebody with an emoji in their name will send input to your system, and then they will get garbage when they see it back. And then they will call customer support, and customer support will say, sorry, computer says no. So let's put it in action. All right. What will it print? I have some utility methods here, but nothing really magical. So what is the length of this string? Who thinks it's 1? Who thinks it's 2? Who thinks it's more than 2? A lot of people think it's more than 2. Well, then I guess 4 is the option, right? Who thinks it's 4? All right, 4 then. Let's see. Well, it is 2, actually. So the definition of the length method and how most of the string methods that don't really take Unicode into account in Java work, they based the results on the fact that Java internally stores strings as UTF-16 encoded. So a char type, the character type in Java, is a representation of a UTF-16 character. And when we have this emoji, like we showed on the slides, it's combined of 2 UTF-16 surrogates. So this is what our Java method length returns. This string has 2 words or 2 chars, which are the low and the high surrogate. And it gives you 2. Well, then if it has a length of 2, then I can get a substring of it, right? What is that? Well, that is garbage. You cannot have a surrogate free floating in the air. You cannot show a surrogate. You just get a question mark. Hey, I missed something because there's something interesting here too. So if we use the code points approach with instead of the length, you can see that is 1 code point, which is beyond beyond 2 bytes. But in the code points world, it's just a 1 code point. And back to our substring. Let's have an actual look what is inside that string. So if we ask for the characters for the char type, we get 2 characters, the surrogates, and then the substring is the high surrogate. So again, whenever you are doing substring, think about malicious input. There might be somebody with a poop in their name. Okay, so you apply to Google and they tell you, because that's what apparently they do every day, you have to reverse a string. Don't use any libraries. Do it. You write a string reversal method, which goes from the end to the beginning of the string, character by character, and well, reverses it. Easy peasy. You even use a string builder. You don't use a string plus. And you think you got the job when, as the input, you get, again, emojis. When you try to reverse it, you again get question marks. And now the question mark is why? So let's look at this. The code points of the original input, we have 2 of them, right? Nothing suspicious about that. Now, when we turn those or read those code points as chars, like we saw before, each one of them is made of 2 surrogates. When you start reversing, you reverse char by char. So the last one goes here and so on. And you can see, by chance, the high surrogate of each one of those emojis is the same. So when you reverse them, you get this thing in the middle, and by chance again, this represents the toilet seat emoji. So this bit can get converted into a proper code point here in the middle, but it is surrounded by free-floating, meaningless surrogate code points that cannot be represented, and this is how you get the question marks. Well, if you do want to do it correctly, you don't even need to use any utility libraries. Just do a string builder reverse. And it handles code points internally. Well, what I said about making sure that the writer and the reader agree on the encoding let's see what gives when you don't agree on that. So we have a string, again, a string that is not trivial. And how it is encoded in as bytes. Well, UTF-8, we already analyzed that. UTF-16, well, there's something interesting here. Instead of 4 bytes, if we just say UTF-16, we get 6 bytes. So once you go into UTF-16 and UTF-32, you can have the words and the bytes in different orders, because you have big endian and little endian. For UTF-32, the default is big endian, and if you don't say, it's big endian. If you don't say for UTF-16, you should declare it using the byte order mark. So you get 2 additional bytes saying, hey, this is going to be big endian, or if you swap them, if it's FFFE, this is little endian. And you can see none of those encodings are the same, really. And here's the platform default, which by chance is UTF-8, as everyone's should be. So let's try to encode and decode different words from different scripts using one encoding and decode it using another encoding and see what happens. Well, it's a bit of a long output, but with basic ASCII words, well, if you try to decode it as UTF-16, you get some Chinese characters. If you have if you think it is UTF-32, you will just get garbage, and so on and so forth. You can see that the encoding and decoding always have to match, otherwise you get garbage. The nulls just cause some spacing. So if you encode as UTF-32, there will be just a lot of nulls. And then if you try to read it with UTF-8 or UTF-16, then you just get blank spaces, which is, of course, also disrupting. And the same happens with extended ASCII characters. They might get converted to some Korean script or some unpresentable garbage. And Korean script turns into some Chinese characters and something else. And well, if you just start sending emojis, it becomes a total mess if you decode it wrong. So make sure that the encoder and the decoder know what is the standard. Now, these two look the same, right? I think everybody already feels there's a catch to it, so I'm not going to ask, what do you think it's going to print? Because we know it will print false. Why does it print false, though? There are different ways to create characters with diacritical marks. You have just the character, U umlaut, uppercase, and you have a letter U, and just a free-floating umlaut, and you can combine them. That way you can build up different characters. So even though they look the same, they are not the same. The first one is just a plain U umlaut, and the second one is a letter U. The first byte is a byte of a letter U, and then after that comes something. Something that means a free-floating umlaut that should be combined with the letter that precedes it. However, if you are processing text, you are not in full control of the input maybe. You would like to normalize that to a certain format. Maybe the actual representation of the character, or maybe the combined character. So there are 4 ways to normalize Unicode characters that have those diacritical marks. The canonical decomposition, which decomposes the letters into their base letter and the diacritical marks. The canonical decomposition followed by composition. So first it does this, and then it tries to combine it back to a single character. And then compatibility decomposition and compatibility decomposition followed by composition. Right now with this example, they look exactly the same, compatibility and canonical. However, we have this kind of fun stuff. Has any one of you seen FFI written like that? Or, well, most of you have seen this one, right? So you can spell I as IJ, or you can have a single character to represent I. And if you write a dictionary, for example, these two should be the same. They should be in the same place of the dictionary, right? Somewhere between I and J. You don't want them to get thrown out at the end of dictionary. So they should be the same, but they are not the same code point. You can even see on the screen that they are written differently. And ligatures are in typesetting a nice way to put letters together so that they kind of float more, so that this I and J is more combined and those FFI are like glued together. So if we compare the normalized forms of those ligatures, we see that if we just use the canonical decomposition and composition, nothing really happens. FFI are those 3 code points. The FFI ligature is a single code point. Cool. But with the compatibility decomposition, this ligature gets split into the base letters. And then you can treat it as FFI individual characters. And the same for the letter I. With the canonical approach, these are 2 different things. With the compatibility approach, it becomes I and J separately. Well, having that in your hand, you can mush it all up. So it has its own name, Zalgo text, which is like this mystic, evil text. You can just squash those free-floating diacritical marks onto a base letter and get this. And you get 54 code points in this little string. Well, if you want to avoid that, although I'm not sure if our zebra example would be happy about it, you can strip accents. And you get the base letters with just a length of 10. Now, everybody likes emojis, so let's do some emoji stuff. There is a boy likes a girl, they get a baby, or even 2. How is that possible that it all fits into a single character? Or maybe not. So let's see. A single code point of a man is connected with a single code point of a woman using this connector code point. And then you can add another connector code point with a child. And that is actually a girl child, as far as I can see. And you can add them a boy child. You can see that it's a different code point. So that way you can grow and grow and grow your family. However, there's a limitation of what the font can show. So I was surprised a bit that when I ported this code from my Mac, on the Mac, the boy and girl emoji, it shows as 2 separate faces. Here, using this font on Windows, it shows as squashed into a single family, let's say. And some fonts, they just don't handle that at all. They will either show you garbage or nothing or question marks. So there has to be a glyph in the font to represent a code point. And you can see that the length method of this family character, it says it's 11 cars, but there are just 7 code points. right? Because those emojis are UTF-16 2 words. Now let's have a look at an astronaut. So this nice emoji of an astronaut is also a combination of something. We recognize this code point as the combining mark, but also there are two code points before it. Let's try to figure out what that is. So you can see that an astronaut is a woman who is originally yellow, but we want to make her, I don't know, Mediterranean maybe? Or tanned? So we add this skin color code point. It modifies the code point that sits before it. And this is how you get all those different skin colors, thumbs up and thumbs down emojis on your phones. Yeah, it's a variation of the skin color of the emoji that sits before it. And then we combine it with the combination code point with a rocket. Well, who is a rocket? Who is a woman sitting in a rocket? She's an astronaut, of course. And that's how you get the astronaut emoji. All right. Once again, the most important thing, remember to agree between the reader and the writer on the encoding. And if you can remember half of what I said today, you will have a great conversation piece at work and with your friends. Thank you very much. Any questions? We have time. Yes?
If you would switch the code points of the boy and the girl, would the picture also change?
Interesting. Let's see how much time we have. I think we have 5 minutes. Let's see if we can do that. So I have to do this. I think we wrote Unicode like that, right? No, I would have to let's see if that's gonna work. Maybe I made a mistake, so I can figure it out offline. But theoretically, at least, it should work, right? Because you can combine the people in any order. So also, it might be that probably the font doesn't show that. But perhaps it's something about the way I wrote it. Let's see if I can make IntelliJ help me with that. No. Sometimes when you paste, reverse it. Oh, let's see. One more thing that I wanted to try. Copy string literal. No, it's not gonna help me much. But let's try the reversing. Yeah, we know how. Yay! There you go. So on equal rights, you can have it both ways. Any other questions? Yes.
So this is reversing the encoding, but then to what extent does it depend on the font whether you actually see something that makes sense?
It depends very much. Let's see if I can show this one. Can I choose something here now? Okay. I think if I change this here to, yeah, this one. If I use a different font, then it just becomes garbage. So this font that I changed to, it cannot handle this gluing of the diacritical marks together with letters. It can handle the emojis, but there are fonts that don't have those emojis. And of course, with new versions of Unicode, they introduce new emojis to the Unicode space, and the fonts have to update. So if they don't update, or if your computer doesn't update, then well, you will get a question mark or some weird box. Any other questions? Yes, one more there.
So to sum it up, you can basically create your own fonts and then create your own Unicode characters and then use them in your applications. But is that a great idea or not?
There is space in the Unicode encoding for private use code points. So theoretically, if you really have that use case, you can use any code point from that block and use it for any purpose you would like. And you can internally develop a font and have those code points be interpreted in whatever way you like.
Yeah, but then you have to hope that it's not taken in the next update.
No, these blocks are reserved forever, so they are declared as private use for anybody who wants them. But you have to hope that nobody sends an input from the outside with, within this range and does it disrupt your system in some way. Right? Because what comes in over the wire are just bytes, and somebody can send any bytes they want. A good tester should still. So yeah, maybe somebody will blow it up in the end. Yes?
Yeah, you showed that you can show the U umlaut with either the combination of the U and the umlaut or as a single character code point. Do you prefer either of them, or which one should you use?
I don't really prefer. I think it depends a bit on the use case. If you are writing like I said, if you are writing a dictionary, then you want them in a certain order, right? So you at least have to normalize your words. But which way you normalize them? Well, the ligature example showed that you should rather decompose, and then your umlauts become free-floating. So most of the time, it probably doesn't matter, but it's worth testing for. The single character, they take less space, so there's that advantage. Yes, last one, please.
Are there any advantages of using UTF-16 or UTF-32 above UTF-8?
Any advantages over with using UTF-16 or UTF-32 over UTF-8? UTF-32 is super simple to implement. You saw that. So if you are, for example, you have a task to implement an UTF encoder, well, just go for UTF-32. Probably nobody does that, right? But at least then you know what is always the size of a code point or of a character, encoded code point. UTF-16 is optimal if you go beyond ASCII. So only ASCII is encoded as a single byte in UTF-8. And if you go beyond that, you get 2 bytes. But still, for some code points within the basic multilingual plane, Japanese, Chinese, and Korean characters, you already get 3 bytes. UTF-16 encodes them in 2 bytes. So there's that. Depends on the script you will mostly be encoding. Thank you very much. If you have more questions, I'm glad to chat here. So come on up and have a great conference.